last video we looked at horizontal and vertical strains, and we found that our image was, although somewhat like the original graph, was neither similar nor congruent. But if we do both a vertical and horizontal strain by the same factor, then we get something called a dilation or size transformation. And this results in a figure which is not congruent to the original figure. It's not the same size, but it's basically the same shape. So it's what we call a similar figure. A dilation will preserve angles, but not distances. So if one particular type of dilation, a size transformation about the origin, is particularly easy to do. And so if we replace x by x divided by c and y by y divided by the c with the same c, and the formula, say with the positive c, then we get what we call a dilation by factor c. And again, of course, if c is 1, nothing changes. But if c is bigger than 1, we get a stretch to a bigger figure. And if c is less than 1, we get a compression to a smaller figure. Let's look at an example there. If we take y equals x squared, replace y by y over 2 and x by x over 2, we get a dilation. Okay, now the way a dilation works, everything is expanded out from the origin. Okay, so we're doubling both the x and the y here. The preimage and image are lined up in a line. If it's bigger than 1, the preimage will be closer and the image will be farther away, but they'll be in line with the origin, the center of the transformation of the dilation. So it goes origin, preimage, image in a straight line, and the distance along that straight line is twice as much for going from the origin out to the image as it is from the origin to the preimage. Okay. Similarly, if we take y equals x cubed, replace y by 3y and x by 3x, then we're doing both a horizontal stretch and a vertical. Actually, it's compression, both a horizontal compression and a vertical compression. So the whole thing is compressed 3 times as small in length, in distance from the origin. So in general, the defining parameters for a dilation requires a point for the center of the dilation and a positive dilation factor c, and we move points along the line containing the preimage point and the center, so to get the distance is c times the original distance to get to the image. We're only considering points about dilations about the origin here, so the point is the origin. The image of a dilation is not congruent to the original image, but it's similar to the image. In elementary school, you probably would have said it's the same shape, but a different size. Angles between point and the preimage remain the same as in the image, but all distances are proportional to the corresponding distances in the preimage, and that proportionality constant is the same as that dilation factor. Okay. The only fixed point of dilation is the center of the dilation. So a dilation about the origin will only fix the origin. And the only example of a graph that's symmetry with respect to dilation about the origin would be a line through the origin. But basically we'll not study other graphs of symmetries with respect to these dilations. So you don't have to worry about the symmetries of a dilation very much.